Ever wondered why titanium can turn blue, purple, or gold without any paint at all? No dyes, no pigments, just electricity, chemistry, and a little optical trickery. Today I'll show you how titanium anodizing works, what actually creates the colors, and why it matters in aerospace, medical, and design. Let's start with the basics. What is titanium anodizing? Put simply, anodizing titanium is an electrochemical process that grows a controlled oxide layer on the metal's surface. It doesn't deposit paint. It changes the surface chemistry into titanium dioxide. The important control knob isn't time or a dye bath, it's voltage. Different anodizing approaches exist because people want different things: wear resistance, corrosion protection, or visible identification and aesthetics. Think of it like different recipes for different outcomes. Type 2 for performance, Type 3 when color matters most. So why does that oxide actually make color? The surprising truth: the oxide layer is mostly transparent. The colors come from optical interference. Light waves reflecting off the oxide interface and the oxide/metal interface interfere with each other. The thickness of the oxide determines which wavelengths cancel and which reinforce, so you see specific colors. Voltage controls that thickness. As a rough guide, low voltages give gold/bronze tones, around approximately 16 volts, mid voltages produce blues, approximately 75 volts, and higher voltages push into greens and purples, 100 volts plus. But the same voltage won't always give the same color. Alloy chemistry, surface finish, electrolyte composition, and even temperature all shift the result. That's why anodizing colorful titanium is part science, part craftsmanship. Now let's look at the different flavors of anodizing you'll actually encounter. Not every anodized titanium part is meant to be colorful. There are 3 practical cases to know. 1. Natural oxide, baseline. Titanium forms a thin oxide just in air. It's thin and gives basic corrosion protection, basically the metal's default skin. 2. Type 2, performance. This is a thicker, gray, wear-resistant anodize, typically around 50 to 200 nanometers. Aerospace and medical parts use it for improved wear, better fatigue strength, sometimes up to approximately 20%, and corrosion protection. It's stable, doesn't cause hydrogen embrittlement, and doesn't change dimensions, and many Type 2 processes reference AMS 2488 standards. 3. Type 3, voltage-controlled color. This targets precise oxide thickness to produce color. Thickness can be in the range of approximately 15 to 100 plus nanometers depending on color. Use cases include medical device coating, jewelry, aerospace marking, and industrial design. Pros: permanent colors without dyes and zero-dimensional change. Cons: no universal color standard and batch-to-batch variation is common. Okay, you know the types. How does the actual process look on the shop floor? It starts with prep. Degreasing, remove oils, fingerprints, and residues. Any organic residue becomes a dark shadow in the final color. Acid etching, light etch/activation, helps the oxide form uniformly. It evens out tiny surface variations so the oxide grows consistently. Anodizing. DC power supply applies a target voltage, typically 15 to 110 volts depending on color, for usually under a couple of minutes. The oxide grows electrochemically, voltage to thickness to color. Rinsing and controlled drying. Rinse thoroughly and dry under controlled conditions. Poor drying can leave stains, streaks, or color shifts. Sealing, optional. For Type 2, you often seal pores to improve corrosion resistance. For color anodizing, this is usually avoided because sealing can darken and mute vivid colors. Even with a solid process, things can still go wrong, so let's cover the usual problems. Blotchy or uneven color, usually from uneven cleaning or etching. If some areas retained oil or scale, oxide growth will differ. Wrong final color, often just the wrong voltage, or the part sat in the bath too long/too short. Remember voltage to thickness to color, but time and current profile matter too. Fingerprint shadows, caused by handling without gloves. Organic residue blocks uniform oxide growth. Geometry-related variation, sharp edges, blind holes, or poor electrolyte flow cause local variations in current density, which means local variations in oxide thickness and color. Key takeaway: repeatability comes from tight control. Consistent prep, consistent bath chemistry, and consistent electrical profiles. So, what should you remember if you're specifying or buying anodized titanium? Titanium colors come from physics, not paint. Voltage controls oxide thickness, and different anodizing types serve different goals, from baseline protection to heavy-duty performance to beautiful permanent color. So before you specify anodized titanium, ask yourself one simple question: what is the real goal of this part? Is it aesthetics, is it performance, or is it both? Once that goal is clear, the next step is talking with your supplier about process control, how they manage surface prep, voltage accuracy, bath chemistry, and handling to make sure the results are consistent and repeatable. If you're looking for a reliable manufacturing partner for your titanium anodizing project, RapidDirect offers one-stop manufacturing solutions tailored to your budget and application needs. If you found this video helpful, don't forget to like, comment, and subscribe. We'll continue bringing you deeper insights into manufacturing, materials science, and real-world engineering.